macQsimal, we are using atoms to image high-frequency electromagnetic fields in the gigahertz and terahertz frequency range. Gigahertz fields, also called microwaves, are a very important part of modern technology. For example, cell phones and wireless devices communicate with microwaves. At the University of Basel in Switzerland, we are developing the tools to make these microwaves visible. And as a sensor for the microwave, we use atoms. The atoms are inside this miniaturized glass cell, which has a very thin wall, so that we can bring them very close to a device we want to study, such as this little circuit here. The atoms can then respond to the microwave field, and we can image this response with a laser onto a camera. An important feature is that we can tune the atoms with a magnetic field so that they are sensitive only to a specific microwave frequency. And from the response of the atoms, more precisely from their quantum state, we obtain an image of the microwave field distribution.
In macQsimal, we have measured microwave near fields at different frequencies, for example at 15 GHz, which has applications in satellite communication. The spatial resolution is tens of micrometers, which is much smaller than the wavelength of the microwave. Alternatively, we can also image the frequency spectrum of the microwave to realize an atomic spectrum analyzer.
In our laboratory at the University of Basel, we have built a first demonstrator of this new technique, and we are exploring the quantum mechanical tricks to further enhance its performance. We are collaborating with the company Rohde & Schwarz to further develop it and eventually turn it into a compact device that is ready for applications.
Terahertz radiation lies on the electromagnetic spectrum between microwaves and infrared, meaning that it sits in a technological gap between electronic and photonic technologies. Here at Durham, we use thermal atomic vapor cells to perform terahertz imaging at very high speeds. We do this by using atoms to convert terahertz photons, which are hard to detect, into optical photons, which are easy to detect. The atoms are excited into an energetic state using resonant laser fields, and once in this high energy state, the atoms relax back to their original state by emitting visible light. If they've interacted with the terahertz field, the light that they emit will be green, which allows us to form a picture of the terahertz field using normal camera technology. Since this process happens over a very short period of time, less than a millionth of a second, we can use this technique to take very high-speed videos at tens of thousands of frames a second. Although this technology is still in the very early stages of development, we've shown that it could potentially be used to inspect the quality of food products, for instance chocolate, or to detect defects in composite materials such as those used to make up wind turbine blades.
In recent years, detection technology of terahertz have advanced rapidly, but traceable calibration of terahertz radiation still remains challenging. In Durham, we demonstrate a system of electrometry in which a terahertz signal can be characterized using a simple principle of electromagnetically induced transparency in a highly excited atomic state, which is the Rydberg state. And we achieve the Rydberg state by applying 3 infrared lasers to the thermal rubidium vapor cell. And then by applying the terahertz radiation on the vapor cell, we observe the ultraton splitting of the atomic spectrum phasor, which is proportional to the amplitude of the applied terahertz field. It has the potential to provide a route to the SI traceable atomic candle for terahertz calibration and, of course, can be used for our terahertz imaging characterization.